All right, so we're going to continue our discussion in section 3.1 of other numeration systems. And I'd like to remind you where we were with the Mayans, since that's where our system leaves off. The Mayans have a very simple structure in terms of the symbols used. They only have 3 symbols. They have a dot that's worth the value 1, a line, horizontal line that's worth the value 5, and a shell that's worth the value 0. The part that makes their system complicated is that when you don't have very many symbols, which they don't, you have to have creative ways of using those symbols to represent different numbers. And so they actually have a place value system, much like we do. We have a base 10 system. Each place has its own value, right? So if I gave you the number 42, the 4 does not mean 4, it means 40, right? As in 4 tens. They have a system like that. Their system is called a modified base 20 system. It's modified because they have the ones place and then they have the 20s place, but the next one's not 20 squared, it's 20 times 18. And then they power up the 20s, so then it's 20 squared times 18, 20 cubed times 18, and so forth. That's why it's called a modified instead of just being a base 20 system. It is written vertically. Vertically, the smallest place value is on the bottom, the largest place value is on the top. And we write dots above bars within place value. So this one is the one that you guys did on the video. Because dots have to come before bars, we know without question that there's a break in place value here because I have a bar and then I have dots underneath it. Okay, so we're not going to put in more bars than are sort of necessary. So like, is it possible that there's a break here and a break here? Well, yeah, it is. We could break every single one of them apart. But unless we're actually told to do so, we're going to assume the fewest breaks exist as are present visibly. So I know for sure there's a break there. I don't know for sure there's any other breaks. Okay? And then dots above bars means those 2 dots over the bar of 5 means I have 7 up here. And the 4 dots above the bar 5 down here means I would have 9 here. And the place value-ness of it is that this is the ones place. So each of those dots and bars multiply by the number 1. And these dots and bars are in the 20s place, so they multiply by the number 20. By ours multiply by the number 10. Okay? So, and then it goes up from there. Okay, so I'm going to jump to example 6 since that's where we left off. If you haven't quite watched all the way through this, please do see those online later. All right, so what we're going to do in example number 6 is we're going to take one of our numerals, 58,532, and we're going to see what does it look like in the Mayan system if we were to write that down. So obviously it's going to look like dots and bars and shells. I mean, those are our only choices of things to look like, but it's going to have a specific structure, and that's what we're going to decide. In order to do this, we actually need to know what their place values are. So I'm going to write them from the bottom up because their lowest place value is on the bottom, right? They have the ones place down here, and then they have the 20s place. Okay, I'd written this a moment ago. And then instead of 20 squared, they have 20 times 18. And 20 times 18 is the number 360. And I'm certain in the video I talked about 360 relating to angles and days of the year and stuff like that, right? That's where that's coming from. And then we do powers of 20. So we do 20 squared times 18, which would give me 7,200. If I do 20 cubed times 18, I get 144,000. And there's no need to go any bigger because 144,000 is bigger than the 58,000 I'm working with. Okay? So as you're taking a look at this, we only need the place values that are smaller than our numeral that we're working with, 58,532. Now these 4 numbers then, we're going to use in that division algorithm. Did I show you one of them like that last time? Yeah, I did in Babylonian, right? So it's going to look like the Babylonian one that we did on the video. So you start with the biggest one that you can divide by. That's 7,200. So we're going to divide 7,200 into our 58,532. Now normally when we do division, we put the divisor on top, right? I mean, the quotient rather on top, whatever goes into it. We say, oh, it goes in 8 times, we put the 8 on top. Well, we're not going to put it on top because I'm going to sort of embed this and do like a stair-stepping down sort of thing. So we're going to put all of our quotients on the right side instead. So if we divide this, and you're welcome to use your calculator. In fact, this is a really good place where your calculator is going to be useful. 58,532 divides by 7,200 how many times? It is 8. And I don't want to know 8 point da-da-da-da. I just want the whole number part. And then I need to actually know how much is 8 times 7,200. So what is 8 times 7,200 or 7,200?
57,600.
So we write the 57,600 underneath and we subtract. So what do we get when we subtract?
932.
Thank you, 932. That's the next thing that we're going to be dividing. Now, the next value that we would divide by going down is 360. Now, even if that number didn't go in at all, it needs to be represented in this hierarchy of steps because it needs to be represented that it went in 0 times. This one doesn't go in 0 times. It goes in more than that. 360 goes into 932 how many times?
Twice.
Twice. And what is 2 times 360? 720. And if I subtract, what do I get?
212.
212. Okay, and we're going to do another stair step of division. Going down from the 360, the next place value down is the 20s place. So how many times does 20 go into 212?
10.
10 times, and 10 times 20 is 200. And if I subtract, I get 12. And the last values, you're always going to keep going until you divide by the number 1, even if you've gotten a 0 remainder at that point, whatever. We don't, we have 12, but it goes in 12 times. And it always will end with a 0 at the end, because we always divide by 1 as our last step. This is the hardest part, is the division part. Because what I need to do now is I need to take each of those digits, 8 down to 12, and I need to write them, I was just trying to slide it, in Mayan form. In other words, I've got the number 8. How do I get the number 8 in Mayan? A line with 3 dots, and the dots are always on top of the line. How do we get a 2, because that's the next one, in Mayan? 2 dots. How do I get a number 10 in Mayan? 2 lines. And does anybody see a problem? If you don't, just hold tight. We're going to talk about it. And then how do I get the number 12 in Mayan? 2 dots and 2 lines. Now, this is correct. We didn't do anything wrong. What we encountered is a system that has a flaw, and probably part of the reasons why we don't use these systems today are the flaws that we encounter. So what's the problem with the way that this came about?
The middle 2 dots, you can't decipher because that is not the next place.
Yeah, there's no way to decipher that those 2 dots are not somehow grouped automatically with the 2 lines that follow, right? There's not. I mean, even if you leave a space, how much space do you need to know for sure that it's not just a little extra space, right? So your book does try to give some space when it's trying to distinguish some of those things, so be aware that it's trying to do that. But in reality, that would have been a very difficult thing if you were writing numerals down in Mayan, and this were that time frame, right? That would be tricky. So the problem, of course, is that this could be eight 360s and 12 20s and 12 1s, right? So this system's better than some of them. It does have a placeholder for 0. We don't have any zeros showing up here, so that didn't have any concerns. But because of the dots and the lines and how they merge together to form different place values, we do end up with some potential problems. So our number here this would be our solution to this particular question. But if you did this, and you wrote out the numerals for 3,252, it would look exactly the same as 58,532. And obviously that's not a good thing, right? Yeah. Any questions about our friends the Mayans? All right, how about Roman numerals? Where have you seen Roman numerals really still used today? There's lots of places. Somebody tell me something. Super Bowl. Yeah. That is not the only place.
Grandfather clocks.
Yeah, grandfather clocks. Mm-hmm. Does anybody read? Sometimes titles and books, right? Mm-hmm, titles and books. Does anybody still take outlines in classes, or does any of your professors give you outlines? Sometimes they're used in outlines. Grandfather clocks. So I'm going to give you sort of an actively engaging question. There's a problem with the clock on the top of Rayleigh Chapel. If you already know what it is, mum's the word. Don't talk to each other. This is not a consult your neighbor thing. If you have an opportunity and you think about it and you're nearby, take a look at the clock on top of Rayleigh Chapel. We're going to talk today through this numerous system, but there is an error in the clock on Rayleigh Chapel. It's actually an error in a lot of clocks, but it is an error, okay? So that's the fun task that you have at hand. You're all like, now, like, what in the world? Just look, okay? All right, so Roman numerals, some of these you're probably familiar with, right? IV and X, I bet you know those. After that, maybe not as much because you don't see them used quite as frequently. So what is the value of the Roman numeral I? 1. How about V? And how about X? Yeah, those are the ones that we tend to remember the most. They occur the most frequently. Those are the ones that do show up on clocks. Does anybody know what L is? It's 50. I believe that it has shown up on Super Bowl at this point. Am I right? Okay, I think that's true. You guys are nodding heads. That's good. Any guess based on the pattern that we're seeing develop what C might be? It is 100. How about D? 500. And M? 1,000. And that's all well and good up to the number 3,000. So up to the number 3,000 and some change, 3,000 plus a little bit more, all of this is sufficient. But anytime you have numbers that are bigger than that, there's a problem because they don't actually write things out bunches of times like we saw with the dots and the lines. So here's the way that they structure their systems. There's two properties. The first one's a subtraction property. To avoid repeating a symbol more than 3 times, that's why we don't have the number 4,000, because I need 4 M's, right? That's why I said 3,000 is my cap. A smaller value is placed in front of a larger one. You may only go one value smaller before a larger value. In particular, this property affects 4s and 9s. So the example is the number 90. Well, the number 90 has a 9 in it, and it's awfully close to the number 100, right? Sure. What letter is the number 100? C. And I want to write something in front of it that will make the 90 be showing up instead of 100. Well, it's going to be an X because it's 10 less than 100. So the X can occur in front of the C. There's only one other thing that it can occur in front of the C, and that is actually, did I say that right? Oh, never mind. I was going to get there in a minute. Sorry. So we'd write XC. 99 was what I wanted to get to next. So what we would like to see, what would be really wonderful if we could do 99 is to put like IC. Wouldn't that be great? 99. It'd be really quick and easy. Well, they don't do it that way. And it really doesn't matter if we like it or not. We aren't Romans and we're not creating the system. We're working from within it right now, okay? So what we're going to do is we're going to treat each of the 9s separately. Okay, so the first 9, as in the number 90, is the same XC that we did before. Okay, that's 90. And then we get the number 9, and we get the number 9 by taking the number 10 and putting a 1 in front of it. Okay? So one way you can think about this is that you're almost treating it by place value the way we do place value, right? Each of the digits has a way to be represented. If the digits are 4s or 9s, you've got a subtraction property in play. Now, the I, for example, and actually let me put this back up. The I can only apply to the 5 or the 10. You can only put an I in front of a 5 or in front of a 10. That will create a 4 or a 9. Okay? The X, you can only put in front of a 50 or a 100 because that makes 40 and 90. They kind of go in these groups, right? So these 3 kind of go together. These 3 kind of go together and have that subtraction ability. And the same thing happens for the number 100. The 100 can go in front of the 500, or the 100 can go in front of the 1,000 to create either 400 or 900. So you cannot skip a whole bunch of these and put the 1 in front of the C. That's what would be nice if we could do it, but it's just not the way that they did it. Okay? So that's the subtraction property. On the other side of not wanting to repeat their numbers too many times, and so they do the subtraction property, they also have a multiplication property. The multiplication property allows us to get numbers bigger than 3,000. So basically anything 4,000 or bigger is going to have a multiplication property of some sort in the problem. That's true. Yeah, the way I said it was right. So if they want the number to be bigger than 4,000, but it's still in the thousands, right? You know, like 5,000 or 10,000 or 20,000, they're going to put a bar on top of the part that's multiplied by 1,000. If they want the number even bigger than that, say like in the millions, they're going to put 2 bars on top. Okay? So for example, this is the number 9,000. 9,000 is definitely bigger than 3. Okay? So what we do is we sort of break it apart in the thousands place and we focus on the number 9. How do I write the number 9? Just plain old 9. IX. So IX is the number 9, and the way that we tell us that it's times 1,000 is we put a bar on top. And if there were things after that, like let's say it said 9,132, you can still have the 9, IX with the bar, and then you can write the 132 just following it without a bar. So 100 is C, 30 is 3 X's, and then the 2 is 2 I's. Okay? So part of it can have a bar, part of it cannot have a bar. You can have double bars involved, doubles and singles and nothing. I mean, like all of those are all possible within the same expression. And you break it apart by where we put our commas is where we really break it apart. Okay, so we're going to do, just like you have seen on the other numeration systems, a value, look at the number before, the number after, and what it is in our system. Before I do that, any questions on multiplication or subtraction properties? Okay, let's see some examples then. MCMX. So the last digit here is an X. And there's not like an I in front of it or something like that, right? So it's just an X. That's our last digit. What is the X's value? A 10. So if I'm wanting to find the number before or the number after, I'm really just looking at the ending value, which is exactly what we do in our system, right? If you want to know what the number before or after the number 952 is, you look at the 2 at the end, and then you decide from there. So we're looking at the X. So if I want to find the number before this, what would I have to do to the X to make that X the number before? Put an I in front of it. So the MCM part doesn't change. But instead of X, I'll have IX to have a 9 at the end instead of the 10. What would I do to get the number after this number?
Put one on the right of the X.
Yeah, so the MCM stays the same. Whoops. And then I'd add the numeral 1 after the X. So I'd have the number 11. Is that all good? So whenever you're seeing these questions about coming before and coming after, they're not asking you to turn it into the number and then add 1 or subtract 1 and then turn it back. That is the long way around things, and that is not what your goal is, okay? Your goal is to work within their system and think, what happens to my last digit as I go up one and down one? C, however, does want us to change this number. So we need to pay special attention to the original number, MCMX, to the placement of values. For instance, we've already said that this is 10 at the end. So let's write these all out one at a time. So what is the M? That's 1,000. What is C? 100. I've got another M, there's another 1,000, and then I had my X, which is a 10. And anytime I have a smaller value in front of a larger one, which I do here, that's subtraction. So this is not 100 and 1,000, it's actually the number, what? Somebody said it? 900, yeah. So I've got 1,000, then there's the 900, 10. 1910 looks like a year. Another place, fun fact, that maybe not fun, but interesting, that you see Roman numerals used is on at least the East Coast in building establishment dates and tombstones. So my brother-in-law actually got married in, I'm not going to get it exactly right, but it's like the church that Thomas Jefferson's buried under or something like that, right? I mean, like it's a very old, beautiful Presbyterian church. And the establishment date is on the door or on the outside of the building in Roman numerals. So you'll see that too in some of the older locations. Oklahoma is not a good example, but East Coast you'll see that in some locations. Okay, we're going to do the same thing that we did back in the Mayan section just a little bit ago. We're going to take one of our numbers, 1,492,019, and we're going to write it in numerals that are Roman numerals. Now, it's important to pay attention to those commas, right? Like, obviously, there's a break here with a comma in the thousands place, and the number 1492 that's occurring before that is definitely bigger than 3. So I'm definitely going to have something with a bar on top. It's really tempting to say there's a break right here, but I don't need there to be a break there, and they wouldn't have used one. The reason is because this one right here, if I ignore all this over here, it's just really 1,000, and I have a way to write 1,000, right? If I ignore the last 3 digits, this number is 1,492, and I can do that without any double bars. 1,000, I just use the letter M, right? So while it kind of looks like there's 2 breaks, because the number before the millions place is the number 1 and not 4 or bigger, like 4 million or bigger, I don't need a double bar. So we're going to look at the number 1,492. So I already gave you the first part. The 1,000 is the number M. How do I get the 400? Okay, so we kind of would like to do 4 C's, but they don't do 4 of anything. So we're going to do CD. So the D is a 500, and then I take 100 away so that I don't have to write 4 C's. Good job. And then I've got 90. How do I get 90? XC, right? I have 100 minus the 10, so the 10's in front of the 100. And then how do I get the 2? 2 I's. 2 I's. And all of that is in the thousands place because it's 1,492,000, right? Like that's the comma that I broke it apart in right here, right? All of this is going to have 1 bar on top of it. But the 19 afterwards doesn't. So how do I write 19? X would give me the 1 in the tens place, and then IX would give me my 9. So it doesn't really matter if there's a space or not a space. Mine kind of looks like I put a space there. I didn't really intend that. But it can't look like it's like you don't go making it merge underneath that bar. We don't want that, okay? So don't go doing that. It definitely needs to be out after the bar part. But other than that, we're good. Okay, any questions on that? Okay, I want to show you a manipulative that's showing up in our next section. So if you've experienced or played with base 10 blocks before, that's what we're looking at here. Base 10 blocks have some manipulatives. They're very helpful for children when they're starting to look at numbers that are bigger than than a single-digit number. So within this system, we have units, so they look like little red squares. Okay, just a little red square. You can do these with Lego pieces as well if you want something that actually clicks together. So the little units like that, so they look like a little bitty square. You have longs, okay, because we have a base 10 system. 10 of the little units go together to make a long, okay? And in terms of drawing it, you don't have to draw out all the 10. You're just drawing a long piece, okay? That's a long. If you put 10 of the longs together side by side, you have a flat. So it's a 10 by 10 or like a decimal grid. If you've taken proportional statistical reasoning, you might have seen us use these manipulatives in there before as well. This is a decimal grid when you're talking about decimals. But a flat looks just like a unit, but big. It should look square. Mine's a little bit rectangular, but you know, okay. And then if you take 10 of these and you stick them all together, you get this one. And this one is called a block. It looks like a cube, right? I mean, yeah, but it's a block, 10 by 10. So if you're taking a look here, a unit has the value of 1, a long has the value of 10, a flat has the value of 100. What's a block have? 1,000. I'll draw it in. So it's not going to have quite the same size, but it'll be okay. So it needs to look, three-dimensional-ish. It's not too bad. That's my block. Now here's the thing. There's nothing special about the number system 10. It's the one we use. That's why we see base 10 blocks everywhere. I don't know if this is on the video or not that you've already watched, so humor me if it's not. But what system do you think we would use if you were born without thumbs? You'd use base 8. That's what you would use. Right? You'd use base 8. Or like the Flintstones, I don't know which one they're missing, but they're missing one of the fingers. Right? All the cartoon characters always have a thumb and 3 fingers. They'd use base 8 too. Okay. Base systems. There's base systems used for all sorts of things. Our base 10 is what we use for our, everyday kind of things. But do you know of any other number systems that are actually used in real life? I mean, you do, but can you think of any? Time. So depending on whether you're looking at the seconds and the minutes conversions, that's a base 60, right? It takes 60 seconds to make a minute, 60 minutes to make an hour, that kind of stuff. If you're looking at the hours into days, you've got a 24 system, right? Base 24. Time's a really good one. Think of any others?
Binary.
Binary. Where is binary used, Caleb?
Computers.
Yeah, computers. Binary has the benefit of it either being zeros or ones, which means it's either on if it's a 1 or it's off if it's a 0. So you get zeros and ones everywhere. You've probably seen movies where they've got like binary code flashing across things and whatever. Ready Player One was one that was recent that had some binary in it. Do you know of any others? There's another computer one, and it's hexadecimal. Hexadecimal is base 16. So that's another one that is used. If you want military time, you could also go with military time using that. So I'm going to pass these around because I think that they're interesting to give you some perspective. And you're going to have, when we get to it next class period, a group work problem that talks about base blocks that are not base 10. So this little box has base 3 blocks in it. Find individual ones. Okay, so the unit looks just the same. No matter what base system you're in, the unit looks like a little block. I mean, it's a little bitty kind of thing, right? A little bitty square. And then it's base 3, so we would stick 3 of those units together to get a long. You're probably saying it's not very long. Well, it's not, but it's 3 long. Right? So this is a long. If you stick 3 of these together, you get one like this. Right? This one would be a flat. If you stick 3 of these together, again, because we're working in base 3, you'd get a block. Looks like the cube. And this box even comes with one more dimension by having 3 of the blocks together. And it makes this one. It doesn't have a name, but it does make this. going to pass it around. Just take a peek in the box, pass it on. It's not a big deal. But there's an example in your homework and maybe group work, well, for sure in your group work, but I think also in your homework that talks about base 5 blocks. And I just want you to realize they're not any different. They're just different size than our base 10 blocks that we use for other things. So if we had base 8, right, we didn't have our thumbs or whatever, and we were looking at what we would do, how much would a unit, a long, a flat, and a block be worth? So units are always worth 1, right? How much would a long be worth in base 8? Yeah, it's 8. So what would you do to get a flat? You'd multiply by 8. So I'm going to write it that way. In fact, it's 8 squared. Right? It's an 8 by 8 flat. Happens to be 64. What would you do then for a block? 8 cubed. And 8 cubed is actually 512. Now, interestingly enough, if we ignore the block and we think about just units, flats, and units, longs, and flats, crayons are packaged this way. They've got some in-between ones. They got some 32 packs and stuff too, 24 packs, but there's an 8 pack. I don't know why. There's a 64 pack. Does anybody like the 64 pack? It's like everybody, it's like make your heart happy because there's so many colors. My kids think that's fun too. It's got the sharpener on the back. Y'all know what I'm talking about. Yeah. So they like to package crayons in some measure of base 8. So if we were looking at this, considering manipulatives, how many units would 237 base 8 be? Well, this 2 right here is in the 64's place, right? It's the flat, right? So this is the units place. This is the longs place, and this is the flats place. This is 2 flats. Well, a flat is 8 squared. This is 3 longs. Well, a long is 8, so it's 3 eighths. And then I have 7 that are sort of just left out, 7 times 1. So if I were to multiply 2 times 8 squared, or 64, plus 3 times 8 plus 7, I would end up with 159. So imagine what's happening here from my crayon perspective. Some poor child walks in with the 64 pack with the sharpener on the back. And they walk in with 2 of them and they dump them on the floor. You know, and then there's somebody else in the room and they just had their little 8 pack because that's all that the school supply list said they were supposed to do. And so they bring over, 3 8 packs and they're all dumped on the floor. And then we had somebody else who just brought 7 random crayons, threw them in the pile. And the question is, how many crayons do I have? It's 159. Okay. So that's kind of the image of what we're working with as we're going back and forth in other bases, is we've got things packaged in certain ways, crayons or otherwise. And what we're doing is we're making a big giant pile of them and we're recounting them the way that we count in base 10. How many units do I have? Well, it's 159. So this question says, or this note at the bottom says, question B is equivalent to asking what 237 base 8 would be in base 10. How many actual crayons do I have? 159 crayons. Okay. Now base 8 is not unique. In fact, base 3 is the one that I sent the blocks around with. And I'd like for us to take a look at how base systems work based on what you know about your base system. So you sort of feel like is supernatural, but maybe not quite so natural when you're first learning it. For instance, base 3 has the number 0, that's fine, and the numbers 1 and the number 2. but there is no 3 in base 3. Right? Once I have 3 of the units all stuck together, it creates a long. Yeah? Think about your image. I get a 2-digit number, right? It moves over into the location where this 3 was, the 3 packs of 8 crayons. So, believe it or not, you will believe it, but there's no 10 in base 10. We call it 10, but it's not 10 because it's a 2-digit number. We do not have a digit representing the number 10. We have 2 digits. And the 2 digits that we use are the numbers 1 and 0. And the number 1, 0 in base 10, we call it a 10. But the number 1, 0 in base 3 would represent its base system, base 3. And the number 1, 0 in base 8 would represent its base system, base 8. And we go from there. After 1, 0, I can have 1, 1, right? I can have 1 long and 1 unit. I can have 1 long and 2 units. But once I put that 3rd unit with it, it creates a 2nd long, and I have the number 2, 0. There are no 3s in base 3. We're going to write a few more out because I want you to see what happens here in just a second. I've got a 2, 1, and I've got a 2, 2. There is no 2, 3. So what would happen next?
Is it 1, 0, 0?
It is. I've run out of 2-digit numbers. 2, 2 is the biggest 2-digit number there is in base 3. Just like 9, 9 is the biggest 2-digit number in base 10. 1 less than what we're in our base system, what our base system's called. And we would continue, and the process would go on from here. So what will it look like then in base 7? Well, much the same. I've got 0, 1, 2. What's my biggest single-digit number in base 7? It's a 6. So I've got 3, 4, 5, 6. And after 6, what will come next? It'll look like 10. We're not going to call it 10 because that's our base 10, sort of language coming through. We're going to call it by its individual digits names 1, 0. Okay, and we're going to go from 1, 0 to 1, 1 all the way up to 1, 6. And what's going to happen after 1, 6? 2, 0. So I know that there's lots of digits. We're not going to keep writing them forever. But what is the biggest 2-digit number in base 7? It's 6, 6. And after 6, 6 would be 1, 0, 0. Now there's some questions in your group work or homework, maybe both, where it asks you to write the first 10 numerals in base 6 or something like that. I don't care whether you start it with 0 or 1. I feel like it's more natural to start at 0, so that's what I do. Your book likes to start at the number 1. So just take your favorite one and just start there and start counting however many you need. 12. All right. How is this question different than the other two?
It's 2 numbers.
It's a bigger number than 10, right? It's 2 numbers. Like 12 is actually a 2-digit number in our system, whereas 7 and 3 are 1-digit numbers. So instead of eliminating digits like we've just done, right, we'll just stop at 6. We actually need more digits. So let me show you what your book does, and then I'll tell you that this is not what all books do. So we've got 0, 1, 2, all the way up to 9. And we need a single digit representing our number 10. That's what we really need. Okay? So what your book does is they use the letter T for 10. And they use the letter E for 11. And they don't ask you any questions above base 12. So there's no need. Actually, they do. They do one more. If they do base 12, they use a W. I think there's a W that shows up. They don't do anything bigger than that. The contemporary math book that I use when I teach this kind of material in contemporary math, which I'm going to start pretty soon, they use the alphabet in order, which I like a lot better. A for 10, B for 11, C for 12, and then you can go as far up as 26 more letters if you needed to, right? So that's a little bit more space to work within. So let's write a few more things out and in this system. So after the E for 11, we do not need a 12 because we're in base 12. So there's no 12s in base 12, just like there's no 7s in base 7. So we move on to our 2-digit numbers, which would be 1, 0, 1, 1. It would keep going. Eventually, I would get a 1T and a 1E, and then a 2, 0, and on. What would the biggest two-digit number be in base 12? EE. Yep. And then I'd need the three-digit number 100. Okay, so let me just make one sort of like throwing it out here comment. We're not doing this because you're teaching this. Some of you are like, I'm not going to teach anything about other bases. I know that. That's not the purpose of doing this in this class. The purpose is to put yourself in a slightly uncomfortable position because base 10 is really comfortable and familiar, and sometimes it's hard to realize the nuances that affect your kids who are not so super comfortable and familiar, right? Kids who say 2011 and 2012, and they're not talking years. They mean what comes after 2019 or like 2009. Well, it's 2000. That's not a good example. It's trying to create an example. Oh, yeah. So where they want it right after 10 is 11. So then you would do 2011 and 2012 because they don't understand the nuances. So that's where we're trying to put ourselves, is in a position to better understand our kids. Okay? We will stop there for today and pick up on Friday.